Hello, my name is Bhavnesh Patel with Infinitum Electric, and I'm here to talk to you about a breakthrough printed circuit board stator technology for EV motors. I'm also accompanied by Paulo Guedes-Pinto, the Vice President of Engineering here at Infinitum Electric. So first off, electric motors haven't really changed in over a century. You look at the motors that were being produced 50 years ago, 100 years ago, they look a lot like one of these. It hasn't really changed. You have laminated iron, you have copper wire, you have a bunch of messy insulation all over the place, epoxy. It's just a mess, and it hasn't evolved. The rest of the components associated with motors, whether it's the power electronics or other components, have certainly evolved, but the core motor, the stator, hasn't really evolved until now. Introducing Infinitum Electric's air core PCB stator technology. What we've essentially done is taken this hunk of metal and transformed it into a very lightweight, very reliable PCB stator. When you make this transformation, you have a number of benefits. One, and probably the most obvious, is the size and weight advantage that you're able to deliver. So going from that traditional iron core to a PCB stator significantly reduces the size and weight. We've made some additional innovations in terms of packaging and in terms of the inverter, which I'll touch on in a minute. This is essentially what the motor looks like, an exploded view of the technology and the product, with the stator in the middle and the two rotors on both sides of the stator. As I mentioned, you have a significant reduction in the size and weight. Just roughly speaking, our motors are generally a third of the size and weight of a comparable radial flux iron core motor. The efficiency is a lot higher. So when you eliminate the iron within a motor, you eliminate one of the sources of electrical losses. And so the peak efficiency, as well as the efficiency over the entire speed torque range of the motor is much higher. So you get a flat efficiency curve versus typically what you see with most other technologies like AC induction, is that you see a steep drop off in the efficiency as soon as you get off that peak that rated speed. One of the other interesting things is cogging torque. So there's a magnetic interaction between the rotor and the stator, and that magnetic interaction results in something called cogging torque. Cogging torque is causes noise and vibration. You eliminate that iron, and you eliminate one of the sources of noise and vibration within the motor. And so our motors are extremely quiet and very low vibration. One of the other areas is around reliability. So if you look at the failure modes for any electric motor, whether it's an electric vehicle or in an industrial application or any other use case, what you'll find is there's a couple of very common reasons why motors fail. One is the windings. So as you're running current through this copper, well, first off, you're taking copper and you're bending it over and over again. And so you're stressing that metal. But then you're heating it up and cooling it down, so you're adding additional stresses. And over time, these windings break. So you have some movement in those wires, and over time, that movement causes the windings to break. The other source of failure is the insulation. So there's a material between the copper wire and the iron. And as the copper wire and iron expand and contract at slightly different rates, that insulation wears and eventually causes that to fail. In our PCB stator, this is made on a fully automated piece of equipment. There's no variability, there's no insulation like you have on a conventional copper wound motor. And so ultimately you end up with a more reliable motor, both in the windings as well as in the FR4 substrate. There's one other area that's pretty interesting. Inverter-driven motors generate bearing currents, and those bearing currents result in premature failure of the bearing system. And in order to avoid that, what you typically find is motor manufacturers will put grounding rings or utilize ceramic bearings to help mitigate those issues. With our motor, given the topology of it, we essentially have eliminated bearing currents from the motor. And so this allows for some additional cost savings in the full system cost. Finally, around power density. So I kind of alluded to this earlier around the fact that we're typically a third of the size and weight. One of the reasons for that is your current density in PCB stator is a lot higher than what it would be for copper wire, and I'll explain some of the reasons for that a little later in the presentation. But ultimately, what that allows you to do is use a lot less copper. You eliminate the iron, and now you're able to essentially get more out of that electric machine relative to previous, traditional copper wound motors. Finally, modularity. So in this image here, we show a single stator approach where we have a rotor, a stator, and another rotor. However, we can stack these on top of each other. So many of our mobility-related applications, we have a rotor, stator, and then another stator, rotor. And that allows us to stack multiple, essentially, motors on a single shaft. And because of the thin form factor, the short length of the motor, you're able to do this and still maintain a very small form factor, much shorter than what you would have for a conventional copper wound radial flux motor. There's a couple of other areas that we've taken a sort of a fresh approach, if you will. We realize this is a little controversial, but we've embedded IoT circuitry into the motor and now inverter. So we actually have sensors built into the stator, temperature sensor, accelerometer. We pull that into our inverter, and we can process that information in real time with our inverter. The inverter generates its own parameters as well, such as current and voltage and other parameters associated with the health of the inverter. And so the combination of the mechanical aspects of the motor and the electrical aspects of the inverter, we're able to derive a lot of insights into the health of that asset. And the one additional step that we've taken is to embed an IoT modem into the inverter. So this is an optional component, but what it allows us to do is not only take that information and deliver insights back to that end user right on without any connectivity or right there at the actual vehicle, but we're able to take that information, push it out to the cloud, and now aggregate this across a fleet of vehicles. And so with that information is that much more powerful and allows you to derive more, further insights into the health of that asset. So as an example, if you start to see the vibration going out of a normal operating range, that may indicate there's a potential bearing about to fail on your vehicle, and maybe that's something that you need to address prior to it having a catastrophic failure. Maybe another example is that you start seeing that inverter drawing too much current for the torque that it's being asked to produce, and so that may mean there's some other potential failure. And so you're able to get these insights with this IoT circuitry and the connectivity built in. And then finally, the firmware updates. So much like what many EV manufacturers, I think Tesla is well known for this, they make new updates available to their users. Our intent is to do something very similar. So this IoT connection allows us to push down firmware updates that either improve the control algorithm or potentially introduce new features back to that end user. And so this connection makes it very easy and simple for that end user to see those benefits. So I've talked a lot about a very interesting technology, very exciting technology, but really, why should any EV company or any company playing in the EV space care? Why does it matter to them? Well, if you look at the market and you look at what's going on, there's a couple of prevailing trends. One is increasing need to differentiate based on the range of the vehicle. If you look at vendor A versus vendor B, one of the most interesting things that people compare those two vehicles with is the EV range. And that's going to continue to happen. I think if you look back in history, it may have been horsepower 20, 30 years ago, but the last 10, 15 years, it's been primarily MPG. How many miles per gallon can you get? So essentially the efficiency of the internal combustion engine. But today with EVs, it's really for a single charge, how far can I drive? And that range is directly impacted by the motor technology that you're utilizing, as well as the size and weight of that motor that's driving that vehicle. The other trend that we're starting to see is new entrants are shifting that development cycle. So it was very common, with the internal combustion engine and historically for platforms to last 10 years or longer. And you typically have some, mid-cycle enhancements or some major revisions throughout that 10-year period. But it was still a fairly slow, relative to what we're seeing today, a fairly slow revision cycle. What we're seeing today with new entrants is that as soon as they have an improvement, again, I go back to Tesla, they make that available in their new platform, but then they also, if they can, push it back down to existing fleet of vehicles on the road. And that fast iteration cycle is very common in software world. I mean, everybody has a phone with apps, and you routinely see apps being updated. But that sort of mentality and agile approach to development is starting to bleed into traditionally a very hardware centric development model for vehicles. And so with that, there's a shift in thinking in how do you do development and implement some of those iterations very fast. And I'll talk a little bit about how we can help on that front. Finally, the other trend that we're starting to see is around, with the adoption of EV powertrains, the vehicle's becoming a lot quieter, a lot less vibration, and it's forcing a lot of the other auxiliary systems to become quieter with lower vibration. And that's one of the areas that, again, we can help with in reducing that noise and weight and vibration of those auxiliary systems. And weight, again, is the other aspect. So these auxiliary systems are being tasked, tier 1 and tier 2 suppliers are being asked to make those auxiliary systems smaller and lighter for that same reason, for that EV range reason. So how are traditional manufacturers responding? Well, one is a significant investment in resources, both capital equipment as well as people, to try and figure out how do we make these motors, whether it's the powertrain or auxiliary systems, lighter and quieter and less vibration. And so it's driving a lot of vertical integration into this market, where previously you may have just bought a component from an external supplier. It's becoming the differentiation in your offering, and so you're starting to, what we're seeing is people bringing that in house. However, we're also seeing folks, take a hybrid approach. I think the Ford Mach-E is a perfect example, where the rear axle motor was an internally developed motor, whereas the Ford motor was an externally sourced motor. And so we're starting to see, a balance of, where it makes sense, utilize internal resources, where it makes sense, utilize external resources. There's a couple of challenges with that model, though, and there's some opportunities too. One of the challenges with that model is when you use external resources, you lose a little bit of control on that design process. One of the opportunities, though, is that utilizing external resources, sometimes you get introduced to new design tools, new simulation tools that can help get you to market a little faster, and that can become a competitive differentiation if you get to market first with, for example, the first electric pickup truck or the first electric the Mach-E or whatever that might be. But that ability to react very fast becomes a differentiator. One of the challenges to that model, though, is you're still stuck with the traditional prototyping process. You still have to adjust your tooling for those new laminations. So if you're in that prototyping stage, you're not doing serial production. You're trying to produce a couple of units to test a concept maybe, and you still have to adjust the tooling to accommodate that short run of laminations. As an example. By the way, the laminations that I'm referring to are the steel within the stator. Another example is the winding. So these windings are typically made on automated pieces of equipment. Well, in order to do that, you need to reconfigure that equipment to accommodate the number, the windings. So as an example, if this motor had, let's say, 60 teeth, and within the stator here, there's these gaps, and these are called teeth. If you had 60 teeth in one design, and now you want to go to 64 teeth, well, that's a whole new reconfiguration of that winding machine. And that takes time and energy and debugging to get that going. And then there's always the rest of the sort of auxiliary components to make the machine work. So you need the motor housing, you need the shaft and bearings and everything else. All of that takes time and effort. And one of the things that we can do is help compress that time frame. One of the ways we do that is with our internal software application called AutoFLUX. AutoFLUX is a really interesting tool. We initially created it to help us with design. So every motor we've produced, we've collected just a treasure trove of data on the performance and characteristics of that motor design. We've input that into a tool that it now allows us to create new designs more efficiently. But it does a few more things than that. So we can go in there and say, I need a 250 kilowatt motor operating at 20,000 RPM with 800 volt input voltage. And maybe there's some other constraints there as well. The tool then spits out a number of solutions that we can then choose from. The tool takes it a step further, though. It with each one of those respective solutions, it simulates the results. So it gives us information in terms of what is the expected temperature rise, what is the expected efficiency of that motor, what are the other characteristics in terms of the physical dimensions, as well as what's the estimated production cost of this motor. So all of this is with a couple of clicks. We input this data. A few minutes later, we have all of this information out. And working with our client or partners, we can then present these results and come to a decision very quickly. Does it make sense to continue this investigation? Maybe the cost of the motor for that particular application isn't feasible, or maybe that the temperature rise of our design isn't feasible, or whatever the case might be. We're able to get those insights and get to sort of a stage gate approach where we can make a decision to say, does it make sense to proceed or not? And if it does, the next step the tool does is it actually automates the Gerber file. So electrical engineers design file, PCB design file is called a Gerber file. It automates the Gerber file. Once it's complete with the design file, we email that off to a PCB shop. We have a number of partners that we're working with there. And within a couple of weeks, we can get a fully built PCB stator back in-house. And so you think about this and you contrast this to making a custom motor, for prototyping, it's world of orders of magnitude different in terms of time and effort. And so we can get from concept to design to simulation and prototype production in a very, very short amount of time, and allow partners to determine if this is the right fit for them, and if it is, be able to test that product in an actual application. Again, the rest of the machine is a very simple construct. We're not looking at a complicated housing. We're not looking at any of the complicated components there. So it's very simple to put together. We're taking this technology, this software, and this PCB stator, and one of the areas we're applying it to is mobility applications, and that's one of the reasons why I'm here presenting to you today. One of the things that we've done more recently is testing oil-cooled a motor. So our first motors were all air-cooled for air-cooled applications, but more recently we had tested oil-cooled. And what we found was a dramatic increase in the current density of this PCB stator. So again, we had an advantage starting off of our air-cooled versus a conventional air-cooled. But with the introduction of oil cooling, we have a further advantage even over a conventional motor being oil-cooled. And I'll go into a little bit more detail there. The other is around noise and vibration. So as I mentioned, and then weight. So as I mentioned, with EVs, obviously noise and vibration is a key concern, and our motor excels in that regard. And then finally, around scalability. So this technology, we've scaled it from a small car seat motor, so the controls for an automatic car seat, to previously this technology was scaled up to 3 megawatts, to a very large system, 3 megawatts. So it's very scalable in that sense. Same for speed. We're working on applications that are down from a couple of hundred RPM all the way up to 20,000 RPM for a traction application. So it's very scalable in terms of both power and speed. And then same with voltage. 400 volts, 800 volts. It's as well as down to 12 volts for the car seat. It's not an issue at all. So we're able to easily take this up and down that most mobility application requirements. Just going back to the oil cooling, this is a really interesting aspect of this technology. So copper wire has a very well-known sort of current density associated with it. It's typically in the range of just any copper wire. Just generally, it's in the range of about 2,500 to 3,500 amps per square inch. You contrast that to, and then with oil cooling, so you do a lot of traction motors use oil cooling to cool the end turns of the windings, and you're able to bump that current density up to there's an error here that it's actually 5,000 to 7,000 amps per square inch. Now you contrast that to a PCB stator. A PCB stator has a current density of 9,000 to 12,000 amps per square inch. And with oil cooling, we're able to bump that up to 27,000 to 36,000 amps per square inch. So why is current density so important? Well, that's what determines how much power you can essentially run in your stator. And so one way to think about this is if you have let's just say a 100 horsepower motor that's air cooled, with oil cooling, that same motor, you could theoretically run that at a minimum 3x the power. So take that 100 horsepower and run it at a 300 horsepower rating as an example. So this is all well and good, but how does it compare to what's available today in the market? This is really interesting, really exciting, but the market's been using induction motors for 100 years, and maybe more recently using synchronous reluctance motors. And so how does this compare? Well, this is a couple of facets of what we typically see in terms of what customers are looking for within a motor. Let's start with the peak efficiency. So I differentiated peak and full range efficiency. But in terms of peak efficiency, synchronous RM is definitely slightly above what most other motor topologies can allow. So what we are typically seeing is a synchronous RM, permanent magnet synchronous RM motor is typically seeing around maybe 96-97% efficiency, which is right around the range that we're getting as well, around the 96% range. Induction motors, though, we typically see slightly lower efficiency. And then probably the more important thing than the peak efficiency is the full range efficiency, meaning at various speed torque points, what does the efficiency look like? And this is one area where we excel significantly above any other technology on the market. Because of the elimination of the iron core, we have a very flat efficiency curve. So throughout that speed torque range, we tend to maintain a very high efficiency curve that's very close to that peak efficiency that the motor was designed for. And typically what you see in induction motors is a steep drop off. So as you reduce that speed and load, you see a drop off in that efficiency. Synchronous RM tends to maintain a slightly better efficiency, but there is still a drop off there. The other is around noise. I think I've talked about this already. And then torque density as well, I've touched on. The bearing currents is one other area. Again, inverter-driven motors generally develop bearing currents that results in premature failure. We avoid that with our topology. The other is around the actual assembly of the motor, and manufacturing of the motor. So this is a very simple motor to put together. This is just a very simple 3D plastic model. But what I took off just now was the top half of the housing. This red component is the bottom half of the housing. And we have a rotor on the top, rotor on the bottom. We have our stator that goes in the middle. And then we have steel disc and magnets on the underside. Which brings me to cost, so material cost. So this is one area where I think AC induction motors tend to excel. You're typically only using steel and copper to make that motor, so they certainly have an advantage there. And it's been around for a long time, so there's some scale in terms of the production costs there. Whereas we're still a small company, so we don't have that buying power that you might typically have with a larger company. And so our material costs are going to be slightly higher than what you would be able to produce with an induction motor. The other aspect is this is a permanent magnet motor, so we do have additional costs there with magnets that an induction motor wouldn't. But that, again, would be the case for an IPM-SynRM motor as well. You typically have magnets there that add to the cost. So just wrapping up here, what we're seeing is that automotive OEs and suppliers are being driven to innovate a lot faster. New entrants are driving that. new innovations are driving that, and so trying to keep up with the market is forcing the automotive companies to innovate a lot faster. Consumers are demanding a lot more in terms of range, noise, vibration. And then Infinitum's Electric's PCV Stator, as well as paired with our approach to how we partner with people, is allows companies to iterate a lot faster and reduce that time to market. So if there's any interest in working with us, would love to feel free to reach out at info@infinitumelectric.com. But we'll open it up to some questions here, and again, I have Paulo Guedes-Pinto with me to help field any questions, both commercial and technical. Thank you for your time, and I look forward to hopefully chatting with some of you further.